Let me preface this video by saying it is heavily inspired by this Codeforces blog by IsThisFFT. I saw his post and was inspired to make it into a YouTube video, not only for the fun of it, but so that perhaps it might reach more people. And I'll leave a link to his blog post down in the description. Graphs are ubiquitous to computer science and can be used to model almost anything. Cities connected by roads, squares on a chessboard, anything which is connected in some sort of way. Different graphs can have properties which tell us important information about their underlying data. We need to be able to find such properties in a reasonable amount of time, even with graphs on the order of magnitude of millions of nodes. In today's video, we will look at two famous algorithms produced by Tarjan, and we'll see how the DFS tree can help us understand them both. But before we do that, let's understand how we form a DFS tree of a graph and note an interesting property about them. Let's take a connected graph like this one and start the DFS algorithm from any vertex. If we highlight every edge used in the traversal in green, we can see that there is exactly one path from the root of the DFS to any vertex, since no vertex is ever revisited. Therefore, we have a spanning tree, a selection of the original graph's edges that connect all the nodes, but does not contain cycles. These edges are eponymously called the span edges of a DFS tree. If we add into the spanning tree the edges that were unused in the DFS, known as back edges, we now have the DFS tree of the graph. There can be many different DFS trees of a graph by processing nodes in a different order or starting from a different vertex, but all will share these common properties, as we will see later. Properties that are difficult to find on a graph can be easy to find on its DFS tree, as we will find out shortly, but first let's make an observation about the back edges on the tree. The first observation to make is that the back edges will always connect a node to one of its ancestors. It will never connect two nodes on different branches like this. To explain why, let's keep this supposed edge in here and think about what must have happened in the DFS traversal for this edge to be there. Remember that span edges show the order that the traversal visits nodes, and back edges show the edges that are discarded because the node has already been visited earlier on the path. So, if there is a back edge here, one way of it occurring is by traversing down this left branch after the right branch was already visited. So let's try visit the right branch first, and oh wow, the supposed back edge was just used as a span edge. It's actually impossible to visit the left branch after visiting the right branch. Similarly, let's go down the left branch, and we see that the same thing happens. In either scenario, the edge becomes a span edge before it becomes a back edge. Therefore, a back edge like this cannot exist. This property of back edges makes it easy to decompose a graph into its DFS tree, and will make it easier to reason about its properties later on. So now let's move on to the first algorithm. A bridge in a graph is an edge such that when it is removed, it disconnects the graph. For example, in this graph, the bridge is highlighted in red. Let's find the DFS tree of this graph. Can you notice what's special about the bridge? If we remove a span edge and there is not a back edge going over it, there is no longer a connection between the two sections of the graph, so it becomes disconnected as shown here. Likewise, if we do remove an edge and there is a back edge over it, then the two sections of the graph are still connected by that back edge as shown here. So a span edge is a bridge if and only if there are no back edges that pass over it. But what about the back edges themselves? How can we tell whether they are bridges or not? Remember that the span edges of the DFS tree form a spanning tree of the graph. The removal of back edges can't do anything to stop the span edges from keeping the whole graph connected. Therefore, we know for certain that a back edge can never be a bridge. So now let's look over the implementation. There are many different ways of doing it, but I'll go over my preferred one here. So first, for each node U, let's store a value depth. This is the number of steps we are away from the root of the tree. To assign depth, we can simply set the depth of a node to the depth of its parent plus 1. Secondly, for each node, let's store a low value. This tells us the node with the lowest depth that we can reach from this node by going down 3 span edges and up through at most 1 back edge at any point. To assign the low value of a node, we can consider the low values of all its children and the depth values of any of its ancestors connected to this node by a back edge. With this information, we can reason that a span edge is a bridge if and only if the low value of the lower node in the edge is equal to its depth. If the low value of a node is equal to its depth, it means there is no bridge going from below the node to above the node. So, as the bridges are highlighted in red here, you can see that every bridge goes up from a node which has an equal depth and low value. Let's move on to the second algorithm. An articulation point is a node such that when it is removed, the graph becomes disconnected. In this graph, 1, 3 and 6 are the articulation points. And this is what happens when 6 is removed. As you can see, 7 is disconnected from the rest of the graph. It's very similar to finding bridges. In fact, we'll use the same depth and low values to find the same as before. But in this case, we know the node being removed must have at least one child, and one of its children must become disconnected when it is removed. Can you figure out the condition? Take a look at node 6. In the section of the graph below and including 8, there is a back edge passing over 6. So when the 6 is removed, that section of the graph stays connected. However, we also see that in the section of the graph below and including 7, there are no back edges which pass over 6. So when 6 is removed, that section of the graph is disconnected. All it takes is for one such child in the graph to become disconnected for the node itself to be an articulation point. So let's begin with the same code as before, which calculates the low and depth values for each node. All we need to do now is add a condition checking whether any of the children of a node have a low value of at least the parent's depth. This would mean that no back edge connects their component to the rest of the tree, and so would make the parent node an articulation point. Here the articulation points are highlighted in red, and each one has a child whose low value is greater than or equal to the depth of the parent. There's just one flaw in this algorithm. Suppose the root of the tree only has a single child. Then, the root is no longer an articulation point since there's no two components that the graph disconnects into when it's removed. So we just need to add one check at the end to see whether the root has more than one child or not. If it only has one, we unmark it as an articulation point. All in all, here's the algorithm to detect both articulation points and bridges in a single pass of the graph. Thank you for watching this video, and I hope you liked this format, which is certainly a lot different from usual.